All right, so this is the last section in the mark. It's a great pleasure to introduce you Professor Bertrand Toën from CNRS Toulouse. He's going to speak to us about exponential homotopy theory.
Thank you. Thank you very much for the invitation. I'm very glad to be here on this occasion. Happy birthday, So what I will talk about today has little to do with homological neurosymmetry. I apologize for this. And also, it's very much an ongoing project, so there won't be many results. Oh,
it's okay.
Okay. There won't be anything. Okay.
It's working.
Oh. Okay, good. So it's partially joined with Jos Goiten, and the purpose is to try to construct the homotopy counterpart of certain homological studies of singularities of functions in algebraic writing. So it will have something to do with singularity theory. So in some sense, it is related to the theme of the conference, but it's going to be very homotopical. And it's also a tentative to answer a question that was asked a long time ago by Ludmil, who keeps asking me how to do a non-abelian or homotopical version of vanishing cycles and those things. So it's a tentative answer to this old question by Ludmil. And I got interested in this recently because it's going to be an interesting setting for applications of the Tannakian formalism for infinity categories. That will be a big part of the talk. And this Tannakian formalism for infinity categories is not yet fully established. I will explain to you why, and I will explain how to try to fill some gaps in the literature. Okay, so I start by some reminders on exponential sheaves and complexes. This terminology, exponential sheaves, maybe it's not completely standard. Maybe these are called non-commutative hot structures, or maybe the better part of the non-commutative hot structures. It works over C. This is just a setting which is interesting to cook up definitions, but keep in mind that you should probably do something more fancy in different contexts, like using analytic sheaves, or maybe mixed-shot modules, or maybe actually motivic sheaves, if you really want something that's going to be very powerful. But I will do the talk in a pure topological manner, just talk about constructible sheaves on algebraic varieties. But keep in mind that behind there is this idea that you should do something more fancy. So there is this unity category dx, x for exponential, which is defined to be the category of, it's an infinity category and defined as a Verbier quotient of constructible sheaves, constructible complexes on A1 divided by constant constructible sheaves. So DC of the point, these are just constructible sheaves on the point, and by pullback, I get constant sheaves on A1, and I roll out like this. And by constructible, I will means that the fibers are finite dimensional. It has two concrete realizations. So it's a quotient category, so there is a quotient map, which is a pointer from constructible sheaf on A1 to the X. And this projection has two adjoints, a left and a right adjoint. And these two adjoints are fully faithful. So they can be used to identify this X with the full subcategory of constructible sheaves with vanishing total cohomology or vanishing total cohomology with compactive force. This doesn't mean that these two subcategories are the same. I'm just meaning that as abstract categories are equivalent, and you can pass from one to the other by just Vernier duality on constructible sheaves on A1. Okay. So from even though it's defined as a quotient, most of the time I would identify this category with the subcategory of objects. Probably the one on the left is the most common, but it's sometimes useful to have also the one on the right. And this category comes equipped with a tensor product given by additive convolution on the FN9. So this additive convolution gives a tensor product on constructible sheaves on A1, and it passes through the quotient. because if you do the convolution of two constant sheaves, it's again constant. And so we can use a symmetric monoidal structure on the quotient. And as such, it becomes a Tannakian category. So it's well, I should have put Tannakian in between quoting marks. By this I mean this dx is equivalent to the bounded Dirac category of finite dimensional representation of some group scheme. This group scheme Gx is the Tannakian group of this category. It's a pretty big affine group scheme of a Q. And I will say a little bit more about it later. Okay, this is all classical. Usually it's done by looking at some T structures on the X. So we can isolate an abelian subcategory, and this subcategory of Berger objects is really Tannakian in the usual sense, and this group Gx is just the Tannakian group of this category of Berger sheaves. So this is all very classical. It appears, for instance, in the book of the work of Katz, of course, in the paper of Koncevich-Soiderman, and also Katarkov, Koncevich, Pantel on non-commutative Hodge structures. And it's related to many subjects like exponential sums, periods, non-commutative Hodge theory, and so on. And there are also more recent references. There is a book which is in progress by Fresal and Jossan, and there's a paper by Gallaert and Pepin-Lehaller, which is just a general setting to talk about exponential sheaves in a general setting, so exponential motivic sheaves or exponential constructible sheaves and so on. Now, why this category is interesting is because if I start with a function of an algebraic variety x, I can define an object in this dx by just pushing forward the constant sheaf. This push forward lives in constructible sheaves on A1, and I can project down to the quotient. And this object in the X is something that contains information about vanishing cohomology of X with coefficient in the constant sheaf. So to be a little bit more precise, if F is proper, the fiber of this CF was T of FF. Sorry. At a point T in the affine line is this relative cohomology of X relative to one of the fiber. So you see that as a constructible sheaf on A1, it sees when the topology of xt inside X change. So it's a receptacle for cohomological information about singularities of functions. Sorry?
I think it goes for non-proper F as well.
It's true for non-proper? I don't know. I have a feeling that I need a base change for this. Okay.
At least for non-proper, it's a non-proper area. So this is
yeah, it could be, actually. So the main problem or the main question of this talk is how do you do a non-abelian version of all of this? Now, I'm not going to be interested only in cohomology, but also in homotopy. So I want an algebraic variety to have something that I will call an exponential homotopy type, which is something that's going to live over this base category dx. So this is not going to be a homotopy type in the usual sense. It's going to be an algebraic homotopy type, and it's going to live over the Tannakian category dx. And for instance, there will be an exponential fundamental group. And if you want to try to keep in mind the kind of object this is going to be an affine group scheme with an action of Gx. And algebraically, you can consider this as just being a commutative Hopf algebra object inside the tensor category Gx. Okay. So this is what we're going to construct and try to relate to Tannakian break. Okay, so let's start now to mention the relative construction of this exponential category. So if I have an algebraic variety, I can define dx of x as constructible sheaves on x plus a1, and I divide by the image of the pullback functor, so constructible sheaf that comes from x, that I want to call constant. Okay. So when x is a point, I take over the previous definition, and you have the same phenomenon that the projection map from a constructible sheet from x plus a1 to this quotient has to adjoint. So you can also identify this as a subcategory, true subcategory of a constructible sheet from x plus a1 with no, I didn't put it. With the property that the direct image to x is 0 or the direct image with compact support to x is 0. It has a convolution tensor product because x plus a1 is a group scheme over x for the additive law, and I define like this, where I just push forward with compact support of the external tensor product. And you want to think of an object in this the x category over x as being a constructible family of objects in the x of the point. So if I have an object E, I can take its fibers at various points in x, and I get objects in the x of a1 of the point, sorry. And so you want to pick up objects in this category as the constructible family. And now what we want to do, we want to define what are smooth families. So there is no hope to construct a Tannakian category out of this big category, the f of x, because of the constructibility over x. There won't be any fiber functor. But if we restrict to a nice subcategory of objects that are smooth along x, or locally constant along x, then there is a hope to get something that looks like a Tannakian category. So what I'm looking for is the notion of exponential local system on x. Here's the definition. I say that an exponential sheaf on x is smooth if there is a closed subscheme in x plus a1, which is finite in the plot over x, and so that E has locally constant homologies outside of D. There are some comments about these definitions, maybe. I'm not quite sure it's the correct one at the moment, in the sense that maybe you can impose more conditions on D. One natural thing would be to say that D is also étal over X, but it seems to be too restrictive if you do this. But at least maybe one possible thing would be to say that D has a smooth irreducible component, for instance, that are étal over X, something like that. I don't know. But what I'm going to say is works for this general definition, but I'm not completely sure that this is not true general.
I think it's okay. I think it was
Sorry?
Do you think it was similar operations?
This is what you came up with? Oh, that's good. Yeah. Okay. Yeah, the thing is that if D is étal, then you won't allow the points they want to collapse, and I think you want the point to collapse. So this is the other. So the idea behind this definition is that this constructible family now is not locally constant as a family of objects in the X, but it becomes locally constant when you compose with the fiber functor on the X. So I can be a little bit more precise here. That any such object you can, because D is proper over X, it's flat over X, you can actually take the fiber at infinity. So you can restrict E along X plus infinity and get a local system on X, because this will avoid D. So there is an underlying local system of such an object. I think that's the key point. So it's not a locally constant family of objects in the X, but it becomes locally constant if I just take the underlying local system. So if I take the fiber functor. So let's denote by the X smooth, this full subcategory of smooth objects. And you can check it stable by this additive tensor product. It's also rigid. It's Q linear and it's stable in the sense it's time related. And there is a fiber functor, which is exactly what I said. You can restrict to X plus infinity. That's a local system on X, and then keep a point in X and take the fiber at X. So you get the fiber functor by just taking the fiber at little X infinity. This functor is going to be conservative. So if I have a smooth object whose fiber is 0, then the object is 0. Okay. check this. Here are some typical constructions of smooth objects. You can start with the local systems of x cross gn and push it to x cross a1. These are called the monodromic objects. Here's another construction where you start with D finite flat and you take a constructible sheaf on D whose push forwards on X is a local system. So this can happen that you have something which is not a local system on D, but when you push it down, it becomes a local system. And I can look at it as a constructible sheaf on X cross A1 and project to the quotient, and you can check that it satisfies the property of being smooth because of this property that here, the push forward of L on X is a local system. And here are two other facts. You can also start with the local systems outside of D, and but this and extend it by 0 over D. But this is going to work only when D is finite data, because when you project to the quotient, you have to do something that might destroy the fact that it's a local system outside of D. So this is only true when D is finite data over X. And finally, if I have any object in the X of X, it's not smooth in general, but it's always generally smooth. So it's an open in X where it's smooth. So here are the kind of objects you can construct in this category. Okay, so this infinity category, the X smooth of X is Tannakian. I will say more details about this notion. Over Q, in the sense that, so I gave a definition a very long time ago, almost 25 years ago. And Wallbridge wrote a thesis about this, and Louis also has a part in his book about Tannakian duality over characteristic 0, and Iwanari also has a version. So there are various versions now of this Tannakian duality over fields of characteristic 0 at least. What this means, it means that this category of smooth exponential sheaves on X is equivalent to the category of perfect complexes on a certain stack. And this stack is the stack of tensor automorphism of the fiber tensor. So this object, the classifying stack of tensor automorphism of the fiber tensor is the name of the rational absolute exponential homotopy type of X. Absolute because you'll see that there is a analytic version in a moment. Rational because this is over Q. And exponential homotopy type is because we started with exponential sheets. So that's the first definition of this exponential homotopy type. I say a little bit more in a moment. If you don't know what schematic homotopy types are, don't worry. I will redefine them in the next slides. What is important is that I can project X to the point, and this construction is functorial. So I look at the map from this exponential homotopy type to the exponential homotopy type of the point, and I told you at the beginning that this is just representation of Gx. So I get a map to the classifying stack of Gx. So I have this map. This is just a projection from Xx to point X. And so the geometric exponential homotopy type, as opposed to the absolute, is the fiber equals. And usually we put a little bar on to mention that this is the geometric version. And as it is the fiber of a map to BGX, it has an action of two. So these two things are equivalent. I mean, the data of something over BGX or the data of something with an action of BGX, these two data are equivalent. I can take the fiber of the first, or to recover Xx, I can take the quotient stack of X bar X by Gx.
Is it the same as the GL operating negative degrees?
It's not important, so it's more complicated than the GL.
No, it's a fiber.
The fiber is also not important. Yeah. There is a big fiber in the fiber. But if you take the unipotent completion, I think it's important. Yeah. I'd say more about this. I mean, I won't be. I mean, I don't know very much about how it looks like this X, but there's a little bit something to say. Okay, so what are the main properties of this exponential homotopy type of a Q? If I look at representations of this group, I get smooth exponential sheaves. So these are smooth exponential complexes that are also sheaves, constructible sheaves on X plus A1. So they classify this, the representation of this pi1 classify this. This pi1 is an affine group scheme. It's a very big algebraic group. And if I have any such representation, and I can compute the cohomology of X with coefficient in L, and this is also going to be computed by the cohomology of this X bar X with coefficient in L. And as I said, Gx acts on this X bar, so it will act on this cohomology, and this reconstruct the object in X. Okay. And of course, the Gx acts on the fundamental group of the geometric exponential fundamental group of X. And you have to think of this as the analog of, you know, if you have an algebraic variety of a number field, say, you can take its étal fundamental group, and you can take the étal fundamental group of X bar when you extend X to K bar, the algebraic closure. And this étal fundamental group of X bar will have an action of the Galois group of the base. So this is the analog, except that the Galois group of the base is replaced by this Gx, and this geometric fundamental group is replaced by this pi1 of X bar. Now, what I was saying is that this fundamental group is pretty big, even the geometric version. For instance, it has a big torus part, so it projects on a torus with a group of characters is essentially functions on X. So it's huge. I mean, it's a very, very big co-algebraic torus. So I think it contains much more than this. So this is at least one big part, which is not important. So yeah. And it also contains a copy of the co-algebraic completion of the topological pi1. So it has something to do with the usual pi1 of the variety X. Okay, so we could be happy with the situation, but I want this guy to be defined over Z. Because we want this to be as close as possible to an actual homotopy type, and something over the rational numbers is it's not discrete enough in a way. So I would like to define this over Z and not over Q. And this is where this Tannakian duality thing starts to become messy. So the problem now is that the Tannakian duality for infinity categories, I mentioned some results over Q or fields of characteristic 0. It fails in general. And it fails in general for a reason, is that the actual notion of symmetric monoidal infinity category is wrong for Tannakian duality. So I will explain what is the right notion to deal with this situation. So it's wrong as soon as you work over either fields of characteristic P or a ring which are not Q algebras. Maybe before I continue, I don't know, are there any questions about this first part? So I'm going to try to explain another definition of what's. I mean, I'm going to tell you what's the replacement for symmetric monoidal infinity category so that Tannakian duality can be established. So I start with infinity topos. I mean, I'm not sure why I wrote infinity topos here. It doesn't really matter. It's just the infinity category of stacks for the FPQC topology. And I recall briefly that these are the functors from community rings to Chance complexes with some flat descent condition. And you look at this as an infinity category. Any stack has a quasi-coherent Dirac category. So I can define it like this. If I have any stack, I can take affine scheme over this type, and I take the limit of the category of modules over that affine scheme, so over A. So that's a perfectly fine definition of quasi-coherent complexes and it's like F. Yeah.
The reason what you're saying is symmetric monoidal in the categories is wrong. Is that because is that related to the endomorphisms of the monoidal unit of the infinity algebra instead of
Exactly.
Okay.
Exactly that. Yeah.
Okay.
Yeah. I will comment on this. Yeah. So this definition you can look at the various tensor products on V of A for any A. This is compatible with this limit, so it gives you a symmetric monoidal structure on Q of F. It is D linear because F lives to respect Z. But there is no hope for this category to recover X. And one reason is this. There are two full embeddings. One embeds E-infinity algebras into symmetric monoidal infinity categories by sending A to D of A. And another one sends co-simplicial commutative rings to stacks by some spec construction. And what I'm saying is that this is a problem because there is a natural normalization functor from co-simplicial commutative rings to E-infinity algebras, and this is not complete. So you cannot have at the same time these two full embeddings and hope for Q of F to recover F. I can take F to be one with spec A, Q of F will be essentially D of A, but then I should be able to reconstruct A, but the left-hand side tells me that I only reconstruct the underlying E-infinity algebra of A. And as this forgetful map, this normalization functor is not fully faithful, there is absolutely no hope to recover F in general. Of course, over the rational numbers, there is no problem because E-infinity algebras and co-simplicial commutative rings are the same thing. So, I mean, this normalization functor is fully faithful. But in general, it fails already over a field of data. So you cannot have Tannakian duality with symmetric monoidal infinity categories. It's just not possible. Okay, so what's happening here is that this Q of F is not only a symmetric monoidal category, it has extra operations. These extra operations are left-hand functors of the symmetric powers. So these are usually denoted by LC of N. And one comment is that in general, this LC of N is not what you expect. I mean, it's not, I take the tensor product N times and I take homotopy combined by sigma N. These are different. So the right-hand side is something you can reconstruct purely in terms of the symmetric monoidal category. The left-hand side is something, is an extra structure that you have to give. So the example is if I take just A itself, LCM of N of A is just A, but of course sigma N might have a lot of homology with positioning A, so you see that these two things are not the same. So what I'm saying here is that these LCM alterations cannot be reconstructed purely from the tensor, the symmetric monoidal structure on Q of F. You have to put them in a structure somewhere. Now, if you look at this operation, you want to think of some extra structure on Q of F. The way I like to see them is that these are categorical version of Frobenius lifts. Because in K theory, they use this advanced operation. So you want to think that these are normally functors from Q of F to Q of F that are kind of Frobenius lifts in some sense. Now, here's the vague definition of what's an LC tensor or LC monoidal infinity category. It's a Z-linear symmetric monoidal infinity category together with some extra operations that we call LC that satisfies a bunch of natural compatibilities. And this is a vague definition because we try to express these compatibilities and it's not so obvious. So this is a definition that we just keep in mind because we think it's nice, but this is not concretely what we need. But this is what you should keep in mind, that there is a way to express what's an LC structure on a symmetric monoidal infinity category. So what the concrete approach we have is kind of stupid in a way. We just consider strictly symmetric monoidal infinity categories. By, for instance, a nice model would be to take categories which are enriched in simplicial abelian groups, and I just take strictly monoidal categories enriched in simplicial abelian groups. So the typical example would be simplicial modules over a simplicial commutative algebra. It's somehow it's a bit suspicious when you first pose a definition like this, because strictly commutative in general is bad, but this actually is working. So if I forget about the Z-linear structure, what's a LC symmetric monoidal infinity category? A model for it is just take a simplicial category with a symmetric monoidal structure which is compatible with the simplicial dimension. Just a genuine symmetric monoidal structure. Nothing fancy like infinity opera, so basic symmetric monoidal structure. So we call them strictly symmetric. I don't know. Yeah, I don't know how to call it. So when you have such a LC tensor structure, it imposes some very strong restrictions. This is the comment you just made some minutes ago, is that the endomorphism of the unit is a strictly commutative space. It's not an infinity space. So as a result, spectra will not form LC tensor infinity categories. So if you take the infinity category of spectra, of course, the endomorphism of the unit is this infinite loop space of the sphere spectrum. And this is not strictly commutative. This is only infinity.
So kind of not respect the linear algorithms.
Exactly. Yeah. We want to avoid working with the sphere spectrum. Yeah. We want to stay resilient. So here is the first result. These LC symmetric monoidal infinity categories, they form an infinity category that's denoted by LC tensor infinity cat. And it's monadic over, say, the infinity category of DG categories over D. There is a forgetful functor, which gives you just a DG category, and there is also a free LC functor that from the DG category construct the free LC tensor infinity category. So the content of this theorem is just that there is a nice homotopy theory of these things. So what's the relation with LC algebras? I mentioned already cosimplicial algebras. There is a more fancy way to talk about them. Is this notion of LC algebras that was introduced by Lucas Brandner and Achille Mathieu some time ago. So if I look at this functor that sends, say, a complex to the direct sum of LC n of E, you can prove that it can be defined as an infinity monad over the Dirac category of abelian groups. And algebras over this monad are called LC algebras, or they are also called generalized rings sometimes. If I look at so these are unbounded algebras. If I look at the ones that are only concentrated in non-negative degrees, these LC algebras are exactly these cosimplicial commutative rings. And if I look at the ones which are in negative degrees or non-positive degrees, these LC algebras are exactly simplicial commutative rings. And the content of the work of Brandner and Mathieu is that you can extend this in the unbounded case, which is not completely obvious. I mean, if you think about it, that's yeah. And now the relation with LC algebras is that the functor from LC algebras to LC tensor infinity category sending A to A mod is fully equal. So this is the LC analog of the result that says that E infinity rings fully embeds into symmetric monoidal infinity. It can be replaced by just saying that the endomorphism of the unit in an LC tensor infinity category has a natural structure of an LC algebra. That's essentially the content of this slide. Okay. So let's now define Tannakian infinity categories and state a Tannakian duality statement. So I I will do only the neutral case. This is not really essential, but it's more easy to state. So a Tannakian infinity category over, say, a commutative ring R is a nonlinear LCM infinity stable Peruvian infinity category T, such that T is rigid. So rigidity is just the usual notion. An LCM tensor structure has an underlying tensor structure. It just states rigidity for the underlying tensor structure. There is nothing fancy here. The ring R should be the endomorphism of the unit, at least finite of the endomorphism of the unit. And then you need the existence of a fiber functor. So this existence of a fiber functor is where everything happens. It has to be a LCM tensor functor from T to perfect complex over R, and it has to satisfy a bunch of conditions. So it has to be conservative. Well extended to end objects. This is one of the technical things that appears for infinity categories that doesn't appear in the usual Tannakian formalism. It's automatic in the usual Tannakian formalism. Here you have to add it to the definition. And you want omega to define the T structure for you when you pull back the T structure on R modules. So it means that you want to say it's positive if and only if omega is positive, it's negative if and only if omega is negative, and it has to induce a T structure on T, or maybe the end object of T, and the functor should become T exact. This is a very important extra condition, and it's related to the fact that omega should be flat. We are over a ring, so I have to state some flatness condition, and this flatness condition is reflected in this T exactness condition of omega. This is also something you don't see in the usual Tannakian duality because we work with abelian categories. But it's the analog of the condition that omega should be exact. And that's all. So what are the examples? The first one is smooth complexes on X. So these are constructible complexes of R modules on X, which locally constant homology sheaves. And the second example is the category I defined some minutes ago, this smooth exponential complexes of X with coefficient in R. So I was doing everything with Q vector spaces, just replace Q vector spaces with R modules. And these two things are examples of Tannakian infinity categories in this sense. Sorry? Yeah, you mean the constructibility condition? You have perfect complexes, yeah, sure. Yeah. I'm just taking the time, sorry. I will apply this to Z, so it's going to be more. So for the first example, the fiber functor is just taking a fiber at a close point. It is definitely conservative. The second condition, you have to prove it. I mean, you have to check that it works. So you have to check that but it's pretty clear that if you have a locally constant, a smooth complex on X, if the fiber is in positive degrees, then the whole sheaf is in positive degrees, and so on. So that's how this T structure aspects. Yeah. The second example is the fiber functor is given by its fiber at infinity, and then localized at the point in X. As I said, again, you have to prove that 1 and 2 are satisfied, so it's not completely obvious. Now, this is the size of categories, and Tannakian duality is an equivalence between some categories and some stacks. So now I'm going on the stack side. So I will define a Tannakian gerb over the ring R to be a stack over R, satisfying some conditions. So the first condition is that it's pointed connected, so it has a global point, and its sheaf of connected components is just the point. That's in the start of Tannakian duality, you have this condition for a gerb that it's locally connected, or two sections are locally isomorphic. That's the condition here. I naught of F is the point. The loop stack of F, if I take the space of loops in F base at the base point star, it has to be flat and affine. By this, I mean you should have a flat and non-negatively graded LCM algebra A, such that the spectrum of A is omega F. So that's the equivalent of the fact that you want BG for G an affine group scheme. Here it's going to be a group stack, but it's going to be affine as a stack in this sense. And then there's an extra condition, which is that F should be part local. This is not a condition you see in the usual Tannakian duality over fields, but if you try to extend Tannakian duality over rings, you see this condition appearing. So it's a technical condition saying that this stack F is somehow determined by perfect complexes on F. So the technical notion is part local. And Tannakian duality is a statement that Tannakian gerbs over R form an infinity category equivalent to Tannakian category over R. And this equivalent is realized by if I have a gerb over R, I take perfect complexes with the canonical T structure that exists because of the flatness condition I have in number 2. And the other way, if I have a nonlinear Tannakian infinity category, I can look at the stack of fiber functors, which is, it's an LC fiber functors. And the statement is that these two constructions are inverse to each other and realize an equivalence. So again, if you do this with symmetrical monoidal categories, it fails. So this is why in Wallbridge or Ludi or Iwanari, everything is done over the field of characteristic 0. You could have version over the sphere spectrum, but if you want version over a ring, you need to have this LC tensor vector. Example 1, this smooth shift over X. Let's say that in order the ring R to be Z, this is the case I'm interested in now. So again, this smooth of XZ is just the bounded complexes of shifts of abelian groups with finite and locally constant cohomology shifts. The fiber functor is just taking the fiber at a point, and it's Tannakian, and the Tannakian dual is called the symmetrization of X over Z, which is it's one of these Tannakian gerb over sec Z, which is maybe a little bit hard to describe, but let me give you some ideas of the flavor of this object. It's usually extremely big. So let's take the most simple space, which is the circle. But the point would be that the point is not very interesting. So the circle. This schematization over Z is the classifying stack of an affine group scheme, which is flat. I call it G. And it can be constructed explicitly as the Cartier dual of a formal group. It's not really a formal group. This is why it's not really a hat. It's like a round hat. It's called the extended formal completion of Gn. So I take the multiplicative group and I take the formal completion not only at the 0 section, but I take the formal completion at all possible sections. So the concrete definition is this. Gn round is the colimit of spectrum of A, where A varies in finite flat Z algebras with a map to Gn. So these are like quasi-sections of Gn over spec Z, and I formally complete along that thing. This is a formal scheme in the sense it's a group inside in scheme. So if I take the Cartier dual, it means I take functions on it. That's a pro algebra, and I dualize, right? So I get an algebra, and it turns out to be a Hopf algebra, and I take a spectrum, and this is my G. The functions on this G hat is a pro Hopf algebra, and the dual is a usual Hopf algebra. So that's the kind of thing you get. This group is huge. I mean, and even the unipotent, it has a splitting by a unipotent part and a reductive part, and even the unipotent part has a big algebraic characteristic. So this is just to give you a flavor of what kind of thing you can get, and you can describe the full schematization by just now if I have a general state, I can take the symmetrical group of loops at the base and do essentially the same construction and replace Z by this symmetrical group, I can assume that this at each level the group is free, and I can do something like this for free groups, and you have an explicit description of this schematization of this. And the second example is this exponential homotopy type over Z now. So I start with a smooth exponential sheet with Z coefficient, and it's Tannakian over Z, so I get by Tannakian derivative this Tannakian germ x over Z. The pullback functor from exponential shift on the point to the exponential shift on x gives me a structure map from the exponential homotopy type to the exponential homotopy type of the point. I didn't check this carefully, but I think what is true over Q states remains true over Z, that this is again just the classifying stack of an affine group C over Z, which is flat. I didn't check this, so this is just an expectation. So this GXG now is itself pretty big. It has a copy of the G of the slide before, so that was appearing as the schematization of the circle. And these copies of G is just the global monodromy of if you have an exponential sheaf, it has a global monodromy, which is just an automorphism, and this is given by this action of G here. But it has also a torus with group of characters, additive group of complex numbers. And it has more than this. It has also a non-commutative part. I mean, already over Q, I'm not claiming I really fully understand this, but already over Q, there is a result in Pleasant's book where it claims that already for functions on A1, the monodromy group you get, I mean, the Tannakian group you get for you take a polynomial, you look at it as a function on A1, and you look at the corresponding object in the X, and you look at the image of the Tannakian group inside the endomorphism of the fiber of that thing. Already for polynomials, you get any G element. So this group GXQ, it has quotient any GLN for any n. So it's pretty big. So it contains much more than this G and this torus part. It contains also a very big non-commutative group. And on the geometric version, it's defined as the pullback of the natural point of BGXZ. And I just put a bar to mention this geometric part. And of course, because it's the fiber of the natural point of some classifying stack, it has an action of GXD. So this is what we wanted to construct. So if I have a natural variety X, I construct a Tannakian germ over step Z with an action of a group, which is this GXZ, which is the Tannakian groups over Z of exponential shifts on the point. Not sure what I want to say here. Yes. So just to, of course, the natural question is how you describe this object. It's so huge that it's not even clear what describe means. Let's say a couple of things about I1. So if I have a local system on X and a function, I can define a particular object. I can push the local system along the graph of the function and project to exponential sheaf, and this will be a smooth exponential sheaf. You want to think of it as exponential f tensor L in a way. And this construction gives you a map from the exponential homotopy type to the schematization across this big torus, whose group of characters is the additive group of functions on X. And this, on the level of Pi1, is this objective. So it gives you already a huge abelian part in Pi1 of the exponential homotopy type, which is the abelian part of Pi1 of X plus this group of characters. Now, if I look at the fiber functor at X plus infinity, I get the map in the other way. So I get the map from the schematization to exponential homotopy type. So this schematization appears as a red hat. So it sits inside. So this exponential homotopy type is an extension of the schematic homotopy type. It is at least as big as the schematization. Okay, so I'm just about to finish. So what we want to do with this now is maybe you know that there is this Tannakian geometry philosophy, and there are results, including recent results, where various types of Galois groups, including the motivic Galois group, can be described as automorphism of some functors. So the classical result is that the Galois group of another field, or maybe the absolute Galois group of Q, is the automorphism group of the functor sending a variety to its geometric fundamental group. This has been extended to motivic Galois group by IU 2 years ago, recently. So there is a question, I mean, can you do the same thing for this exponential by one story? So here, again, I'm thinking about the fact that you should redo everything motivically, not only for constructible sheaves, but for motivic sheaves. And then you have this group GX, which is the exponential motivic Galois group that controls exponential motifs over the point, and you want to write it as the automorphism of this functor sending X to this geometric pi one, geometric exponential pi one. So that's one thing we would like to check. And there are, in the same vein, there is also a relation with rational points, because one reason to introduce all these homotopy types was the existence of something that I call the non-abelian algebraic maps. So this is a map from rational points of a variety over, let's say, any field K to the connected component of homotopy fixed points of Gx acting on the geometric part of the exponential motifs. And that's interesting because it gives you it defines for you a filtration of rational points by looking at this non-abelian spectral sequence, which exists by some general nonsense. And for étale homotopy, there is a very nice paper by Andrew Spall showing that this the information you get on rational points that way, just using the étale homotopy type, is actually stronger than anything that was previously studied before, like the Breuer-Manning obstruction and this kind of thing. So you really get new things that way. Well, you see, pilot is a set. So it's a spectral sequence, but some of the groups are just non-abelian, and some of the groups are not even groups. They are just pointed sets. So you have to, but you can see what it's just. You do positive curve on the homotopy type, and you look at fixed points, and there is an obstruction from one stage to another, and so this is just an. So there is a, I don't know, maybe Dwyer in Kant maybe has a notion of non-abelian spectral sequence. It's a spectral sequence, but in low degrees you have non-abelian groups and pointed sets. So yeah, so already in the homotopy type there is something interesting happening. In the motivic homotopy type there is certainly something interesting happening, and the guess is that using this exponential homotopy type we get more. So that would be an interesting thing to check. And the last question, which is what about moduli spaces? So by this I mean moduli spaces of objective X, for instance. It's unclear to me how to do this. I mean, it sounds silly because this category, the X of the point, is pretty explicit. But as soon as we talk about families, there is this D inside X plus A1, which has, for which sometimes points collapse. And the representability of the moduli functor you can write down is not clear. So what does it mean to have moduli spaces of these smooth exponential sheaves? It's not clear to me, but I think it's important at some point to have. Okay, so